So this is a video demonstrating the design or the dimensioning of a secondary clarifier according to the description and guidelines given in the wastewater treatment compendium by Peter Maribo. I assume that you have read, prior to this example here, have read the compendium page 39 to 46 describing the method. The method described in the compendium is based on some heuristic data and is as such a generic method, but it's not a standardized method, it's not an approved method, such as, for instance, the ATFAO 131 or other authorized methods, but it demonstrates how you can design or dimension a clarifier given some necessary set of criteria and giving some design information. So the method description is found in this handout, also that we're going to look at the design criteria. So what do we know about how much hydraulic load does the clarifier has to deal with? What is the concentration of sludge in the aeration tank? What kind of sludge do we have? How well does it settle? And then there is a procedure that we'll go through how to find out how big a clarifier will be able to deal with this and safely and effectively separate the sludge from the wastewater given the hydraulic conditions and the sludge settling conditions. In this example, I will use a relatively small plant. It will be a maximum peak hydraulic load of 300 cubic meter per hour. There will be a dry weather load, maximum dry weather load of about 180 cubic meter per hour. We assume we have an aeration tank that has up to 5 kilograms of suspended solid per cubic meter. And the outlet criteria from the clarifier in this case is going to be 30 milligrams suspended solids per liter as conditional standard. That is pretty much equal to the standard European Union requirement, and this will be okay with the criteria given in the compendium that says, well, we can with this design go down to 20 milligrams suspended solids per liter in average. Furthermore, I'm doing some assumptions here. I'm assuming that this clarifier, or I'm designing a clarifier that can manage a sludge volume index sludge up to 130 milliliters per gram. So that means the sludge settling quality must be at least as good as this in the peak load situation for the clarifier to function. So that's an assumption. Secondly, I assume that the sludge will behave something like the example given in the compendium, this curve 5.8, where we have a sludge concentration of 5 kilograms per liter and an SVI of 130, and we see how does the sludge concentrate over time. So if we leave the sludge, settled sludge, it will slowly settle more and more, and the concentration of suspended solids in the sludge will increase over time. So this corresponds to an initial starting concentration of 5 kilograms and a 30-minute concentration equivalent to a sludge volume index of 130 milliliters per gram. So this is my assumption as well, that this is the case. And finally, I will design my system so that I will have a return sludge flow that will be equal to 85% of the inlet flow, or at least it must be possible to achieve as much flow for the return sludge as 85% of the inlet flow. So if we take a look at the clarifier, well, we have a circular clarifier, we have an inlet flow to the clarifier, which is equal to the inlet flow to the plant, plus the return sludge flow that goes back from the clarifier to the inlet of the process tank. So this is the inlet we've got. We have a sludge concentration, which is equivalent to the maximum sludge concentration in the process tank. We want a low concentration of solids in the outlet, and we have to return then all of our settled sludge, or almost all of it, so that we have a sludge balance that says that whatever comes into the clarifier is equal to what goes back to the aeration tank. This is a slightly simplified mass balance because we also have an outlet from the clarifier to the treated wastewater, and also an excess sludge production that will remove solids from the clarifier. However, these two parts are much smaller than the return sludge flow. And a simplification also made in this system is that we say we have a uniform concentration of solids in here, which is not true. The inlet concentration will be slightly smaller than the outlet concentration because we will have a growth of biomass in the system. And the assumption why this simplified mass balance is okay is because we say that what goes out with the treated water and the excess sludge is equivalent to the net growth of sludge in the system. That makes our simplified mass balance acceptable or right. Okay, so back to the system here, we have an idea of we have the design criteria given, and now we need to start following the procedure. So first step in the procedure is roughly to estimate the size of the clarifier by using an overflow rate of 1 meter per hour. So how big an area would I get using an overflow rate of 1 meter per hour? So 1 meter per hour will give me the overflow rate is defined as the inlet flow divided by the area. So that means if that's 1 meter per hour here, I can find the area as equal to the inlet flow divided by the overflow rate, and that's, in this case, it will be the maximum inlet flow because this is going to be the maximum overflow rate. That must be less than 1 meter per hour. So I have 300 cubic meter per hour divided by 1 meter per hour, so that gives me an area of 300 square meter, and that is equivalent for a circular tank for a diameter of approximately 20 meters in diameter, a little less than this. Okay, so I know that I'm looking for a clarifier that is in the order of 20 meter in diameter here. Next step is to choose a side water depth for the clarifier. There's always a number of designs that will satisfy all my criteria, but I need to make some assumptions about the size of the circular clarifier, and I need to choose a side water depth. And in this case, I'll say, well, for a size like this, I will go for a side water depth of less than 3 meters. I can go and take a look at my criteria here in the compendium and see, well, for clarifiers less than 25 meters, well, I can choose different side water depth and get different set of criteria. I will choose a total depth of, let's say, 3 meters. And then I know I need to leave a little freeboard above the water, so that gives me my effective depth of the clarifier of 2.7 meters. So I choose the effective depth, in this case, to 2.7 meters. That's a design choice. And this will result in criteria. The set of criteria given here for the 2.7 meter deep tank with a diameter less than 25 meters. And I can see the 4 criteria I need to fulfill is that my overflow rate in a storm situation has to be less than 1.1. In the dry weather, less than 0.8 meter per hour. My solids loading rate has to respect 2 numbers, both in the peak load situation in the storm situation and in the more average like dry weather load situation where I actually really need to comply with my outlet criteria. Okay, so I have 4 criteria I need to respect, and that means I can calculate 4 different areas that all has to be that will be the minimum area that could comply with these 4 criteria. So I will do this now. The first area will be respecting overflow rate maximum of less than 1.1 meter per hour. So that's in the storm situation. So, and since the overflow rate is defined, as I wrote before, as the inlet flow divided by the area, that means I can calculate a necessary area to fulfill this criteria. That will be equal to, the area has to be bigger than 300 cubic meter per hour, my peak flow, divided by the criteria 1.1 meter per hour, which is the criteria I have here for the maximum overflow rate, the storm situation. This will give me an area requirement of 273 square meter. Then I will check the criteria, the second criteria, which is the criteria for the overflow rate in dry weather maximum load. That will give me must be less than 0.8 according to the criteria in the table. So that will give me an area which had to be bigger than the dry weather maximum flow, 180 cubic meter per hour, divided by 0.8 meter per hour, which is equal to an area of 225 square meters. So we can see a smaller area here. So this criteria is more critical than this dry weather criteria. Third criteria, according to my table here, is the solids loading rate maximum in storm situation of 10 kilograms of suspended solids per square meter per hour. So the solids loading rate is equal to the total flow to the clarifier divided by the area. So that gives me an area requirement here, which has to be bigger than the total flow. So that's the inlet flow plus the return sludge flow times the return sludge concentration. That's my solids load in kilograms suspended solids per square meter per hour. And then I divide by the acceptable solids loading rate, so the SLR here. In this case, for the maximum situation, I will get an area where I have 300 cubic meter per hour times 1.85, because my return sludge flow would be 85% of the inlet flow, and I have 5 kilogram suspended solids per cubic meter, or up to that, and my solids loading rate, acceptable solids loading rate, was 10 kilogram per square meter per hour. So if I punch in the numbers here and just to make sure I've got the figures right, I get 278 square meters here. I have to do the same for the dry weather situation, and in this case the area, the flow is 180. I have the dry weather situation criteria for the solids loading rate to be 5.7 maximum. So again, 85% of the inlet flow is return sludge flow. And this is cubic meter per hour. And I divide by my new set of criteria here, which was 5.7. And that gives me a area requirement So 180 times 1.5 is 5 divided by 5.7, so 292 square meters. So now I can compare my required areas, and I have to choose the bigger, because this area here will make sure that all my criteria are satisfied. So if I choose this area, I will get a dry weather solids loading rate of 5.7, which would be just acceptable. I will get a slightly smaller maximum solids loading rate than 10. I will get an overflow rate that is considerably smaller than 0.8, which will be acceptable, and slightly smaller than 1.1 in the storm situation. So this area is sufficient with the 2.7 meters of height. So that means an area like this means that I have a diameter of 19.2 meters. That will be the clarifier that will do the job here. So am I done yet? No, not quite, because I still have to do some checking. If we take a look at the list of criteria, we can see I have to check the requirement for all overflow and solids rating. And now I have to do a check of whether my hydraulic retention time is more than 1.4 hours, because this is a criteria as well. I need to find out via the sludge mass balance if my clarifier will not be filled up with sludge more than 50% of the volume, or if any of these criteria fail, I need to choose a different, basically a different area, a bigger tank, maybe a deeper tank, or I need to play with the return sludge flow, which is also something I can choose. I have chosen 85% of the inlet flow, but I could make it bigger. Either change in choice here will lower all my critical values and give me a better design. So I'm looking for the smallest acceptable clarifier. So if I'm looking at the hydraulic retention time, it has to be bigger than 1.4 hours. And if I'm calculating this, the hydraulic retention time is equal to the volume of the clarifier divided by the total flow that goes through it. So both the inlet and the return sludge flow. So the volume will be the area times the effective height and if I put in numbers here, I have my 292 square meters times 2.7 meters, and this has to be complied with at any situation. So this will be my peak flow, 1.85 times 300 cubic meter per hour. Calculating this value gives me a value of 1.42 hours. So just a little bit above the criteria. And I will say, well, it is, if I round off, I will get the right number. I'll get 1.4. So this criteria is just acceptable, just okay. Now I also need to check my sludge mass balance, and I need to see if my sludge in the critical situation does not take up more than half of the volume of the clarifier. And for this I need to look at my sludge mass balance, and I need to look at the sludge settling curve that I have found and set to be the one that I believe I will get here, to see if these values will satisfy my criteria. So I could do this in different ways. I'm choosing to look at what, if I have a peak flow situation here, what will be the time I have for the sludge in the lower half of the clarifier. So I will say that this half, the lower half, will be where I can the space I can fill up with sludge, and this sludge will move downwards to be pumped out of the clarifier. Over my 50% of the volume I will have clear water, or water where I can allow sludge and water to separate and sludge to settle freely. So if I have 50% of the clarifier filled up with sludge, how much time will the sludge have to concentrate in this volume? This concentration time is then equal to the concentration volume of the clarifier divided by the flow going out. And the volume that I would allow the sludge to concentrate in would be half of the total volume of the clarifier. So the total volume I had before, I had 292 square meters, and I had 2.7 meters of depth. And I had my return sludge flow in the peak situation 0.85 times 300 cubic meter per hour. This gives me a concentration time that I can calculate. .55. So in the clarifier, if I allow the sludge to actually take up half of the total volume of the clarifier, this sludge will go down towards the outlet, the return sludge flow outlet, and that will allow the sludge to stay in here for 1.5 hours. The question is, what kind of concentration will I then arrive at? To answer that, I will have to look at my sludge concentration curve. So if I take a look at this and I say 1.55 hours, that is equivalent to 93 minutes. I'll need to go in here at my sludge concentration curve and find approximately 93 minutes and make a reading here to see, well, what kind of sludge concentration could I expect giving the sludge 93 minutes to settle. And that means that the concentration at the very bottom, because the sludge is moving slowly down, and as it moves down because it's pumped out, it's getting more and more concentrated because it stays there longer and longer time. So it starts out with 5 kilogram per cubic meter, and the longer it stays, the concentration goes up. And I can see I'm ending up with something close to 11. Let's say we have approximately perhaps a reading here that says I get a sludge concentration of 10.8 to 10.9, something in that order, kilogram suspended solids per cubic meter. So this is a possible sludge concentration. Now I need to check if my sludge mass balance can be kept giving this concentration of the return sludge. So my sludge mass balance say that my return sludge flow plus inlet flow times the concentration in the process tank should be equal to the return sludge concentration times the return sludge flow. If I'm not, with this concentration, able to pump back as much as I have in the inlet, I'm in trouble. So looking at things with these numbers, this number over here should be at least as big as this. If it's bigger over here, that's okay. That just means that I don't need to concentrate up to the maximum. I could have a sludge level that's less than 50% and hence a smaller concentration time. So I'm going to see if the number over here is bigger than the number here. Here I had 300 cubic meter per hour times 1.85 times 5 kilogram suspended solids per cubic meter. And over here I have, let's say I use my value of, let's just say I use this number here for security, 10.8 times 0.85 times 300. So this will be kilograms suspended solids per cubic meter, and this will be cubic meter per hour. So I'm just gonna calculate these two numbers and then compare them. So over here I've got 300, so I've got 2775, and the unit will be kilogram SS per hour. So entering into my clarifier, and on the other side I have 2755 going out of my system. If this was a design that was concluded here, I would see that I would actually have more sludge going in than going out. And that is not a balance. So what would happen in reality is that I would be adding to the volume of sludge here in order to achieve a longer concentration time, and hence a higher sludge concentration that could fulfill my balance requirement. But it's not allowed for me to go up to more than 50% of the maximum volume according to the design set here. So this, the conclusion to this is that I need a deeper clarifier, or I need a larger clarifier, a bigger area. But I can also see that I'm pretty close, so I'm roughly where I am supposed to be. So the question is how accurate I can actually design things, and I can say, well, maybe I should choose a clarifier which is slightly bigger or slightly deeper, recheck my numbers, and end up with that. So maybe I should have a total height of 3.5 meters. That would give me much more volume for the sludge. It would give me 25 centimeters more. It would give me longer time then, and then I would probably reach a level where my sludge balance could be achieved. And then I have successfully checked all my criteria, and I've got a design that is acceptable according to the design method here. So a clarifier of 19.2 meters, 3.5 meter depth, or maybe slightly bigger, and then sticking with my total 3 meters and an effective depth of 2.7 meters. So that's it.